This is the second part of the presentation on the network simplex method. I will continue the network simplex method at step 3. In the previous video, we have solved the example up to step 2, with the conclusion that the current BFS that we obtained in step 1 is not optimal yet, and then the non-basic variable x34, which is currently at lower bound, equals 0, it needs to be increased, or in other words, it needs to be taken into the BFS as a basic variable. So now we're going to do that in step 3. So from step 2, we know that this BFS is not optimal, and then we need to enter the non-basic variables of x34 into the BFS. Now in step 3, what we need to do is that we need to identify a cycle, which involves the non-basic variables that we would like to enter into the BFS. So here you can see the cycle looks like this, from 3 to 4, and then 4 to 5, and then 3 to 5. So in this moment, you don't really need to care about the directions of the arc. You just see that these nodes, if you connect them together, it will create a cycle or a loop. Okay, now what are we going to do with that cycle? So let me erase this a bit. So what we're going to do with the cycle is that first, we are looking at the non-basic variable that we would like to enter to the BFS, x34, because it is currently I mean this, because currently x34 equals 0. In the new solutions, we want to increase it from 0 to something, from nothing to something. So we are going to add a value to that x34, which we here symbolize it by theta. We don't know yet how much theta is, but we just put theta. Now look at the arc. If we add the flow from 3 to 4 as much as theta, it means that the consequence is that from 4 to 5, the flow will also be increased by theta, right? Because you're increasing 3 to 4, automatically 4 to 5 must be increased as well. Now look at the other consequence. If we increase from 3 to 4, which is currently nothing, to become theta, it means that we're taking away some of the flow that is going from 3 to 5 originally. So from 3 to 5 originally we have 1 unit of flow. Now we are going to take this away, so it becomes 1 minus theta. Why we're taking away flow from 3 to 5? You need to pay attention to the direction of this flow. See, the direction of this flow is 3 to 5, and then we're taking some of those flow away from 3 to 4. So obviously the flow from 3 to 5 will be reduced by as much as theta. So let me summarize. First, you identify a cycle, and then on that cycle you work on the logic. Here you need to increase by theta, which is the consequence. This is also increased as well, and then the other consequence is that here the flow will be reduced as much as theta. Okay, so now the problem is we need to check how much theta should be. So from the arc 3 to 4, we can increase theta as much as 5. Why? Because in the current solution it is 0, but the maximum capacity of the arc from 3 to 4 equals 5. So theta equals 5 for the arc of 3 to 4. Check all the arcs in the cycle that we have. In the arc 4 to 5, currently the flow is 4. We can increase as much as up to 6 unit of flows. So theta for the arc of 4 to 5 equals 2. Now for the arc of 3 to 5, the current flow is 1. And then how much we can decrease this flow? The answer is 1 because you cannot have a negative flow, right? From 3 to 5, currently you have 1 flow. If you want to decrease or reduce it, the possible decrease that you can do is 1 at most. Now consider all the arcs in the cycle. You take the minimum of these 3. So the minimum of 5, 2, and 1 equals 1. So theta equals 1 for the entire cycle. And that's how we're completing the step 3. Now in step 4, we simply implement what we've got in step 3. In step 3, we got the theta equals 1. So here x34 from nothing to become 1. And then the consequence 4 to 5 from 4 becomes 4 plus 1 equals 5. And then another consequence from 3 to 5, 1 minus theta, theta equals 1. So now it becomes nothing. So there's no flow from 3 to 5. So that's the end of the step 4. And then step 4 says we need to go back to step 2. So let's do it. So in step 2, we're computing the y's for all the basic variables again. And then for each non-basic variable, we need to check their c hats. And then from there, we can say whether the current BFS is already optimal or not. So this is current basic feasible solution, the current solution that we have from step 4, and we're going to check whether this is optimal or not. For all the basic variables, use this formula, yi minus yj equals cij. So the basic variables in this case is x13, x34, x25, and x45. How do I know that these are basic variables? You can see that they are drawn with solid arcs, so it means they are basic variables. And then use this formula. So x13 means that yi minus y3, x34 means y3 minus y4, and then x25 means y2 minus y5, and then x45 means y4 minus y5 equals to the Cij. Cij is the cost, which you can see in the very first picture in the problem. Is the cost of flowing 1 unit of flow through an arc ij. Now remember that you always need to set y1 equals 0. After you set this y1 equals 0, now you can solve these remaining equations for the y's. Okay, and this is the result for all the y's. Next, we are going to use this y to compute the c hat for all non-basic variables. So we have two non-basic variables at the upper bound, which is x12 and then x14. How do I know that they are in the upper bound? You can see they are in dashed arcs. And for non-basic variables, this is the formula to check the c hat, yi minus yj minus cij. So for the non-basic variables, x12, you check c hat 12, and then for the upper non-basic variable x14, you check c hat 14. And then apparently they are already greater than or equals to 0. So for the non-variables at the upper bound, they're already okay. And then check the non-basic variables at the lower bound, which is x32 and then x35. Okay, because there's nothing here from 3 to 2 and there's nothing from 3 to 5, so they are non-basic variables with the value equals 0 or at the lower bound of the capacity of that arc. So use the same formula again, this, and then you get the y's from here. So you just plug in yi minus yj minus cij. So for example, C hat 3, 2 equals y3, which is minus 12, minus y2, which is minus 12 as well, and then minus C32 that you can see from the very first graph in the problem, the cost of flowing 1 unit of flow from 3 to 2. And then the result is already less than or equal to 0. It's the same thing for C hat 3, 5. It means that for both non-basic variables at lower bound, it's already okay. Since everything is already okay, both for the non-basic variables at upper bound and non-basic variables at lower bounds, everything is okay means that everything satisfies the optimality condition. So in other words, our BFS here is already optimal, and then we can stop the process. We have obtained the optimal solution. So this is the optimal solutions. We have the basic variables, which are all arcs, which are drawn with the solid arcs here. So x13, x34, x25, and then x45. Okay. And then we also have non-basic at the upper bound. So x12 with the dash arcs, and then x14 also with the dash arc. And then we have the non-basic variables at lower bound, which means that x32 and x35 equals 0. That's why you see nothing in the drawing. Okay, and then if you check the solution, you can see that the flow through each node really satisfies the net supplies for each node. You can see that the net supply of node 1 equals 10, and then it exactly sends out 5 plus 1 plus 4. It sends out 10 units of flow. And then the net supply for node 5 minus 10, it exactly receives 10 units of inflow. And then the net supply for node 3 is 0 because it receives 1 unit of flow, and then it sends out 1 unit of flow as well. The same thing for node 4. It receives 4 units of flows, and then it receives 4 units from here and then 1 unit from there, and then it sends out all those 5 flows from 4 to 5. So that net supply for node 4 is also 0. You can see that this optimal solution really satisfies all the conservation of flow constraints for all nodes in the network. Now here we have another example of a minimum cost network flow problem. We're going to apply the network simplex method to solve this problem. So the value with dollar signs here means the cost of transporting 1 unit of flow from one node to the other node through this arc. And then the value without a dollar sign means the maximum capacity of that arc. So how many units you can transport through this arc. And then the values inside the parentheses, they are the net supply of the corresponding nodes, which means that 1 will have an outgoing flow of 10, and then 4 will have an incoming flow of 10 because the sign is minus 10. And then for node 2 and node 3, because you see nothing in the parentheses, which means that node 2 and node 3 have net supplies of 0. Anything that is coming into the nodes, all of them must be sent out from that nodes, such that the net supply equals 0. So that's how you're reading all the information in this figure. In the network simplex method, the very first step is finding a starting BFS. So remember, the starting BFS must form a spanning tree and then must have n-1 basic variables. So based on trial and error, suppose you obtain this BFS. It is a spanning tree, 2, 3, because you have 4 nodes, but you only have 3 arcs connecting all the nodes. So yes, it is a spanning tree. you have 4 nodes, but you have only 3 basic variables. So yes, it's a BFS. And then you see that to make this flow logical, you send 5 units of flows from 1 to 3. And then because the net supply of node 3 equals 0, you need to send out all those 5 units of flow to node 4. And then because 5 units here exactly equals to the maximum capacity of the arc 3 to 4, it means that you can see here it is drawn in dashed line because this is a non-basic variable at the upper bound. So before going to step 2, I would like you to complete this all these 3 things here. So from this BFS, make a list. What are the basic variables? What are the non-basic at upper bound? And what are the non-basic variables at lower bound? Try this before you continue to step 2. So in step 2, we're going to compute the y's for the basic variables and then use those y's to compute the c hat for each of the non-basic variables. So for the basic variables, we're going to use this formula here. And then remember that you get the indices of yi and yj based on the basic solutions, based on the basic variables that you have in this solution. So for example, here you have the basic solution of x1, 2. It means that the indices here y1 minus y2. And then you have x2, 4 is a basic variable. So here you have the indices y2 minus y4. And then finally, x1, 3 will give you the indices of y1 minus y3. Okay, always start by setting y1 equals 0, and then you get the Cij from the first figure. Remember the value with the $sign corresponding to each arc. Solving all these equations give you the value for each y. Now we are using those y's to compute the c hat for all the non-basic variables. So this c hat 34 corresponds to the variable at the upper bound, and then the other 2 corresponds to the non-basic variables at the lower bound. Because you see, for example, there's nothing flowing from 2 to 3, so x23 is a non-basic variable at the lower bound. For the variables at the lower bound, it is okay if the value of c hat is less than or equal 0. So it says here they satisfy the optimality condition. For the value at for the non-basic variable at the upper bound, however, if the value is negative, it violates the optimality condition. Because for a non-basic variable at the upper bound, the value of the c hat should be greater than or equals to 0. If there is a violation like this, it means that our basic feasible solution is not optimal yet. Now we're going on to step 3. From the previous slide, we saw that the c hat 34 is negative. It violates the optimality condition for a non-basic variable, which is currently at the upper bound like this. Now it means that because it is currently at the upper bound, we want to reduce the flow that is going from 3 to 4. Currently it uses the maximum capacity from node 3 to node 4. We're going to change it by reducing some of the flow that is going from 3 to 4. In step 3, we start by identifying a cycle before we are doing that increase or reduce thing. Here we want to do something with this arc. Now let's see what are the other arcs that are connected with this arc. So we include x13, and then x12 is also related because they both start from node 1. And then now node 2 and node 4 is also related. So here is our cycle. It connects all the nodes in the network, right? It's a cycle because it forms a loop. When we have obtained the cycle, we start performing what we want. Here we want to reduce the flow from 3 to 4. So originally the flow from 3 to 4 equals 5. We are reducing it to become 5 minus theta. If we reduce the flow from 3 to 4, consequently we must reduce whatever coming into 3, right? So here we also reduce the flow from 5 to become 5 minus theta. Because the net supply of 1 is still the same, 10, if we reduce the flow that is going from 1 to 3, it means that the flow from 1 to 2 must be increased, right? Because the net supply is still 10. If you reduce 1 to 3, it means that here you must be increasing the amount of this flow. So here we write this down as 5 plus theta. And then as the consequence, if the flow from 1 to 2 increase, it means that from 2 to 4, the flow is also increasing. So we write down here 5 plus theta. Now the next step is we are checking what is the theta that can keep the conservation of flow balance in the entire network is still satisfied. So here the theta equals 5 because we can reduce the flow as many as 5 units, right? Currently you have 5 units and then you can reduce it as much as 5 units until nothing flows from 3 to 4. The same logic for 1 to 3. Currently it has 5 units of flows, so you can reduce as many as 5, such that if we do that, there will be nothing flowing from 1 to 3. Now from 1 to 2, currently the flow is 5, but the maximum capacity we know from the original problem is 7, which means that we have the possibility to increase the flow by 2. So the theta is 2. And then same thing for 2 to 4, we see that the current flow equals 5, but the maximum capacity of this arc is 8. So we have the possibility to increase by 3. So theta equals 3. Now to keep the conservation of flow balance for all the network, we need to take the minimum of all thetas here. So the minimum of 5, 5, 2, 3 is 2. And then we are applying theta equals 2 to the entire cycle that we have. So here it becomes 3 because 5 minus 2 equals 3. 5 minus 2 also equals 3. 5 plus 2 equals 7. 5 plus 2 equals 7. So this is our step 4. Now, before going back to step 2, again, I would like you to list what are the basic variables, non-basic variables at upper bound, non-basic variables at lower bound for this basic feasible solution. So I think by now you're already familiar with what we're going to do when we go back to step 2. So using the basic variables, we're going to compute the y's. So the basic variables here are x13, x24, and then x34. We use those basic variables to compute the y's. Remember to set y1 equals 0 and then solve all these equations to get the y's. And then use those values of y's to compute the z hat for each non-basic variables. For the non-basic variable at the upper bound, like x12, it is at the upper bound, we compute the c hat, and then we obtain that the value is positive for the c hat. It satisfies the optimality condition for a non-basic variable at upper bound. For x23 and x32, which are at the lower bound, we also compute the c hats for them, and then we see that one already satisfies the optimality condition. However, for the variable x32, it violates the optimality condition for non-basic variable at the lower bound. Because for the non-basic variable at the lower bound, the c hat should be less than or equals to 0. Because it is positive, it means that we need to introduce x32, which is currently 0. We need to introduce that into our BFS, or in other words, making it has a value from nothing to something. So we want to introduce x32 from nothing to something. First, what we do is we try to identify a cycle. x32, and then x24, and then x34, it is a cycle. And then from that cycle, we say that we want to increase 3 to 2 by theta. As the consequence, here is also increased 7 plus theta. And then if you take away some flow from 3 to give it to 2, it means that this flow from 3 to 4 must be reduced accordingly. So you see here 3 minus theta. Again, you check what is the minimum theta to keep the entire network still at the balance for the conservation of flow. So let's see here that here the theta equals 3 because you can reduce at most 3 units. Here the maximum from 3 to 2 equals 6 because the maximum capacity of this arc is 6. And then from 2 to 4, currently you have the flow of 7 units. The maximum capacity is 8, so here the possibility to increase is only 1. And then you take the minimum among 3, 6, 1, it is equal 1. And then you apply that. So now you see here it becomes 2 because 3 minus 1 equals 2. Here the theta itself is 1, so it is 1 here. And here 7 plus 1 equals 8. Same thing here, I would like you to list what are the basic variables, non-basic at upper bound, and non-basic variables at lower bound. And then always after step 4, you cannot stop. You need to go back to step 2 first to check whether your current solution here is already optimal or not. And then using the same procedure for the basic variables x13, x34, x32, you use them to compute the y's. Then once you solve the y's, again I emphasize that you need to remember to set y1 equals 0, solve the y's using only basic variables, and then use this value to compute the c hat for all non-basic variables. Now apparently here that C12, which is corresponds to x12 in the upper bound, and then C hat 24 that corresponds to the x24 at the upper bound, as well as C hat 23 which corresponds to the x23 which is in the lower bound. Remember x23 is this arc which currently equals 0, so don't be confused between x32 and x23. x32 equals 1 and it is a basic variable, but x23 is a non-basic variable which equals 0. Okay, so you compute the c hat for all those non-basic variables, and apparently they all satisfies the optimality condition. For the one in the lower bound, it's already less than or equals to 0. For those in the upper bound, it is already greater than or equals to 0. It means that our BFS here is already optimal. Now you can stop. So this is the original problem here, and this is the optimal solution. You can see that in this optimal solution, the basic variables are x13, x32, and x34, which are all drawn by the solid arcs. And then the non-basic variables at the upper bound is x12 with the dashed arc, and then x24 also with the dashed arc. And then we also have the non-basic variable of x23. So x23 is this arc. It is a non-basic variable because we flow nothing through that arc. And then you can see that in this optimal solution, the net supply constraint is satisfied. Node 1 is sending out 7 plus 3, which is equals 10, that it should send out. And then node 4, it receives 8 plus 2, so it satisfies the net supply of minus 10, which means that node 4 must receive 10 units of flow. And then for node 2 and node 3, the conservation of flow balance is also satisfied because they have zero net supply, right? Node 2 receives 7 plus 1, it sends out 8, so it is okay. Node 2 receives 3 units from here, it sends out 1 plus 2, so it is okay. And then the optimal Z value, or the total cost of the solution, is $75, which you obtain by multiplying the number of flow, 7 here from x1 to 2 times $4, and then 3 units here from 1 to 3, 3 units here times $3, and then 1 unit here times $2, 8 units here times $3, 8 times 3, and then finally 2 units here times $6 of that cost. So the total cost is $75 for the optimal solution. So that's how we use the network simplex method to solve a minimum cost network flow problem. So this is the end of the presentation of the network models topic. We've seen some optimization problems that can be modeled as network models. We have also seen the methods and algorithms that can be used to solve those problems. Thank you.